Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at number and indices. So let's start by looking at operations with directed numbers. So directed numbers are when we're just thinking of numbers as positive or negative. We need to be able to first add, subtract, multiply, and divide negative numbers. So we have rules here for adding and subtracting. Positive and negative makes positive, negative positive makes negative, and two negatives make a positive. What is confusing about this rule is it means something different when you're adding or subtracting compared to when you're multiplying or dividing. For adding and subtracting, it refers to symbols next to each other. When we're multiplying or dividing, we're talking about the answer. Okay, you're probably a bit confused. Let's go through a few examples to see what I mean. So let's say, for example, you had negative 15 subtract negative 8. So our rule here that two negatives make a positive when we're subtracting refers to symbols next to each other. We have two negatives next to each other without a number in between. Don't worry about this bracket here. So what this rule tells us is that we can change those two negatives into a positive. Negative 15 subtract negative 8 is the same as negative 15 plus 8. So because you're adding a positive, you start at negative 15, you are making the number bigger by 8. So we start at negative 15 on the number line, we go 8 to the right, it's 8 bigger, it is negative 7. If I had, on the other hand, something like 20 plus negative 32, well, once again, when we're adding or subtracting, we have two symbols next to each other without a number in between. A plus and a minus next to each other, we can replace with a minus or a subtract. This is the same as 20 minus 32. Now, when you're subtracting a positive number like 32, you're making the number small. You start at 20 on the number line, you go 32 to the left. 20 minus 32 is equal to negative 12. So when we're adding or subtracting, these rules are all about symbols next to each other. But what about when we're multiplying or dividing? Let's say we had negative 5 multiplied by positive 8. So this time, when we're looking at these rules, they're telling us about the answer. What we do is we go 5 times 8 is 40, so we ignore the signs for now. Now we need to decide, is our answer positive or negative? When we're multiplying or dividing, these symbols, these rules tell us about the answer. This tells us that a negative times a positive is a negative answer. So our answer of 40 needs to be changed to a negative answer. Negative 5 times 8 is negative 40. Similarly for division, if you have something like 90 divided by negative 10, so here we have a positive divided negative. This rule tells us positive divided negative gives a negative answer. So the answer will be negative 10. Now let's look at squaring, which brings a lot of people in. Let's say I have negative 5 squared. Now you know that when you square a number, it's the same as timesing by itself. So negative 5 squared is negative 5 times by itself. So how do we do that? Well, 5 times 5 is 25, and our rules up here tell us when you multiply a negative by another negative, the answer is positive. The answer here is positive, we leave it alone. 25 and positive 25 are the same thing. We don't need the positive sign. So just be aware, whenever you square a number, the answer is never negative. So if you square a number and get a negative answer, you've done something wrong. All right, let's now look at order of operations. So on the previous slide, we looked at calculations in which there was just one operation. We were just timesing, adding, or whatever. Sometimes you get expressions like this that have multiple operations. So that everybody gets the same answer, it's important that we have an agreed upon order of operations, and that is BIDMAS. So you do any operation in the brackets first, then you do indices, which means raising to a power. Now, division and multiplication next. These two are like the same rank. You do whichever occurs first from left to right. And finally, there's addition and subtraction. Also the same rank. You do whichever occurs first from left to right. So when we have something like negative 15 subtract 3 times negative 4, there are two operations. We are subtracting and we are timesing. These two symbols are just negatives. So order of operations tells us which we do first. Because multiplication is higher than subtraction, we do the multiplication first. So it's important we show our working out. I'm going to leave the negative 15 and the subtraction alone. I am not touching them yet. I'm only doing this part here first, the multiplication. So 3 times negative 4 is equal to negative 12. Positive times negative is a negative. Of course, now we have two negative symbols next to each other. We can change them to a plus. So our final answer is negative 15 plus 12, which is negative 3. Note that whenever I use an equal sign, this has to be equal to the previous line, and I'm showing my working by going down the page. It's important that you make sure that things are actually equal when you use this symbol, because when you're doing something like this, a lot of people just do the multiplication and they'll write equals 12 or something like that. This isn't true. This thing doesn't equal 12. So please make sure you don't make that mistake. All right, let's try this one here. So there are a few operations in this one. There is a subtraction, another subtraction, there is raising to a power, and square root. So here's what we're going to do first. We're going to do the brackets first. Anything in brackets comes first. So we're going to replace this 1 minus 4 with negative 3. So my next line of working is I'm square rooting the whole thing. It's going to be the square root of 5 squared minus 1 subtract 4 is negative 3 squared. Okay, order of operations tells us after we do the brackets, the next thing we do is indices raising to a power. So I'm going to raise this to the power and this to the power. So remember, squaring is timesing it by itself. 5 squared is 5 times 5, 25. Negative 3 squared is positive 9. Remember I said before, when you square a number, the answer is never negative, and we still have the subtraction between them. Our next step, let's do the subtraction. 25 minus 9 is 16. The square root of 16 says, what do you times by itself to get 16? Answer 4, and I'm done. All right, let's look at this question. Insert brackets in the statement below to make it true. This is a statement. Turns out it's not a true statement because order of operations dictates that I must do multiplication first, then division. So if I were to go figure this out, I go 9 times negative 10 is negative 90. Divide by negative 2. And then I would do the division. Negative 90 divided negative 2 is positive 45. Well, hang on a minute, negative 8 plus 45 doesn't equal 49. This is wrong. This statement here is not true. If you go and figure out this, you won't get 49. I can, however, change this statement to make it true just by inserting brackets. So what do we use brackets for in maths? Well, the only purpose of them here is to change the order of operations. See, I just figured out when I do the times and then the divide, I get the wrong answer. I don't get 49. So brackets help us change the order of operations. Now, this is not an easy question to figure out where the brackets go. You just have to keep trying different places that will change the order of operations. So I'm going to start by trying to change it so I don't do something like the times first. I could put the brackets here and here. That would mean I do the addition first, sorry. But that still doesn't get me the right answer. 1 times negative 10 divided negative 2 is not 49. Okay, they didn't work there. Let's try somewhere else. So what we can do is instead of putting them here, we can put 1 here and 1 here. This changes the order of operations. I still do the times first, but then I'm going to add before dividing. So this gives us negative 8, subtract 90, negative 98, divide negative 2 is 49. If I put the brackets there, I am correct. These are not easy questions. You just have to use trial and error, putting the brackets at different places so that it changes the order of operations, and you keep doing that until you get the right answer. All right, let's now move on to index laws. So I said before in this video, indices is all about raising to a power. It's when you have something like this, a to the power of b. You would have seen this before. You know, if you have something like 2 to the power of 3 This number here is how many times you multiply this number by itself. So 2 to the power of 3 is 2 times 2 times 2. This is in index form because it's a base. 2 is the base, 3 is the index. This is expanded form. I just tell you, because most of the questions you do, they're going to ask you to write your answer in index form. And that means write your answer as something to the power of something. So these are the 6 index laws you need to know. So the first one just says if you multiply bases, the same base, so here A is the base, then you add the powers. So if you have something like 2 to the power of 6 times 2 to the power of 3, you keep the same base and you add the powers. 6 plus 3 is 9. So this also applies to pronumerals. So if you have something like x to the power of 7 times x, remember x is the same as x to the power of 1. Because raising to the power of 1 doesn't change it. 2 to the power of 1 is 2. 3 to the power of 1 is 3, 4 to the power of 1 is 4, and so on. So x to the power of 7 times x to the power of 1, keep the same base, and you add the powers. 7 plus 1 is 8. So the second index law here tells us that when we divide bases, we subtract the indices. So if you have something like 5 to the power of 8 divide 5 to the power of 3, you keep the same base and subtract the powers. 8 minus 3 is 5. Index law 3 says when you have a power raised to another power, keep the same base, multiply the powers. So if you have something like 10 to the power of 9 to the power of 4, you keep the same base, 10 is the base, multiply the powers, 9 times 4 is 36. Again, it works with letters as well, so y to the power of 3 to the power of 7, you would keep the same base and multiply the powers. 3 times 7 is 21. Index law 4 says anything except 0 to the power of 0 equals 1. So 2 to the power of 0 equals 1. 3 to the power of 0 equals 1. 100 to the power of 0 equals 1. 0 to the power of 0, however, is undefined. You can't do it. If you were to put it on a calculator, you would get an error. But anything else to the power of 0 is 1. Negative 5 to the power of 0 is 1. 2.72 to the power of 0 is equal to 1. So just make sure you're aware of order of operations. If you have something like 3 times 2 to the power of 0, you need to do this one first because BIDMAS, I index, comes before multiplication. So this would be equal to 3 times 2 to the power of 0 is 1. 3 times 1 is obviously 3. Index law 5 says when you raise a fraction to a power, just raise the top to the power and the bottom to the power. So if you have something like a squared over 3 and you raise it to the power of 3, so raise the top to the power, so keep the same base and multiply the powers. On the bottom goes 3 to the power of 3. Now 3 to the power of 3, 3 times 3 times 3, it's not 9, it is 27. And the final index law says when you have a product to a power, you raise everything in the product to that power. So if you have something like 2x to the power of 5, you need to raise the first thing in the product to that power. So 2 to the power of 5 is not 10. It's 2 times 2 times 2 times 2 times 2. It's actually 32. And then we need to raise the second thing in the product to that power. So the final answer there is 32x to the power of 5. Now, sometimes you're going to need to simplify expressions which require you to use multiple index laws. So let's take a look at something like this. So when we're simplifying something like this, we're still going to use our order of operations. So we're going to do the brackets first. So x to the power of 4 to the power of 3, using index law 3, what you do, we're going to leave the 6 alone, we keep the same base, and multiply the powers 4 times 3. Okay, and we're going to leave the bottom alone as well. Okay, but wait a minute, you remember that x is the same as x to the power of 1. So actually, this top part here, x squared times x, becomes x to the power of 13. So I'm going to rewrite that as x to the power of 13. So now I need to go 6x to the power of 13 divide 3x to the power of 8. So when you have numbers and pronumerals, just do them separately. I go 6 divide 3 is 2. Now x to the power of 13 divide x to the power of 8. This fraction line here, fraction lines always mean divide. So when we're dividing bases, x is the base, we keep the same base and we subtract the powers. 13 minus 8 is 5, and I'm done. All right, let's look now at some harder questions. So which number goes in this box here to make this a true statement? Well, let's go and figure out this top part here. So we have a power to another power, and we know that when that happens, we keep the same base and multiply the powers. Okay, now on the bottom, we're just going to leave that as 2 to the power of something to the power of 6. Now we want that to equal 2. 2 is the same as 2 to the power of 1. So what am I going to do now? Well, I know 2 to the power of 32 times 2 to the power of 5. I can simplify that by adding the powers. So 2 to the power of 32 times 2 to the power of 5, keep the same base and add the powers. Okay, so what is going to go here? Well, when I'm going to divide, so I am dividing because fraction line means divide, I know that I need to subtract the powers. So 37 minus 6 times whatever's in the box has to equal 1. This will be 2 to the power of 6 times the box, and when I divide indices, I subtract the powers. So what number goes in there? Well, to go from 37 to 1, you need to subtract 36, which is, of course, 6 times 6. 6 goes in the box because 37 minus 6 times 6 gives me 1. Let's look at this question. Write 81 to the power of 12 as a power of 3. That means I want to write 81 to the power of 12 equals 3 to the power of something. What goes in the box? Well, note that 81 is actually 3 to the power of 4. So 81 to the power of 12 is 81, 3 to the power of 4 to the power of 12. The power to a power rule tells us we keep the same base and multiply the powers. So 81 to the power of 12 is equal to 3 to the power of 48. I don't know what either of these numbers are. It would be a massive, massive number, but they would be equal. All right, let's now look at just one more harder question. All right, so this is another harder question. Which is larger, 4 to the power of 6,000 or 6 to the power of 4,000? No way we could figure out what either of these is in our head, and even our calculators, these numbers would be too big. So we have to use index laws. So what we're going to do is try and write them in a different way. The reason it's hard to compare, hard to see which of these is larger, is the bases are different, and so too the powers are different. See, unlike in the previous question, 6, the larger number, is not a power of 4. We can't make the bases equal. But how can we make their powers equal? Well, we do it like this. See, the highest number that goes into each of these is 2,000. So I can write 4 to the power of 6,000 as 4 to the 3 to the power of 2,000. Because of the power to a power rule, this is 4 to the power of 3 times 2,000. Similarly, this one I can write as 6 to the power of 2 to the power of 2,000. Because of the power to a power rule, I would keep the same base, multiply these together. Now, note that 4 to the power of 3 is actually 64. 4 times 4 times 4, not 12, it's 64. 6 to the power of 2 is only 36. It's 6 times 6. See, this and this are equal, these two are equal. Now it's really easy to tell because the powers are the same. Clearly 64 to a power is going to be greater than 36 to that power. So clearly 4 to the power of 6,000 is greater than 6 to the power of 4,000. This number here will be much larger. All right, thank you so much for tuning into this video. Best of luck studying, but I know you'll ace the test. You're a star. This has been the luckiest maths teacher in the world. Have a great day.